worried because Susie said the wrong time. She said 12:45 come back, which would have been a long time to have gone for a pee.
Obviously, I'm in Europe.
Maybe it was the Mars time that confused us.
Maybe.
We're a bit jet lagged, rocket labs.
Welcome back.
Welcome back. Are you having a nice time? Good. Yeah, we are as well. I hope you've been doing lots of interesting things, and hope you've been asking having lots of interesting discussions in your classroom or wherever you are about the things we've been talking about. We've been really lucky to have such a group of incredible guests.
Yeah, absolutely.
Talking to us.
And we've got more to come.
We've got more to come. It never ends. It never ends. We've got George Dransfield from The Sky at Night with us now. We had Pete Lawrence from The Sky at Night. It's a bit of a Sky at Night themed episode, my old show, The Sky at Night. George, are you there?
I'm here. Hello.
Hey, nice to see you. How's life in the sky at night?
Oh, always exciting. We're going to be back on TV in a couple of months, actually. So yeah, it's getting very exciting again.
Yeah, it is exciting. I was saying to Pete, we had Pete on, and I was saying The Sky at Night is the longest running TV show in the world. It's been going for 13.7 billion years, non-stop, without a break. And Pete's been on all of them. He didn't find that funny. I think he found it. I thought I was insulting him, but I wasn't. I meant it well. Isn't it, just while we're on this, it is an amazing thing, The Sky at Night. It's one of those strange programs that it's been going for so long, and it is so warmly regarded by viewers, I think, and it's become a real kind of cultural institution in the UK.
Oh yeah, absolutely. And I think it's so important because, being the longest running science TV show just means that, people really expect us to always be there to kind of tell them about what's going on in space, what's the new astronomy news.
Yeah, it's great. And you do a fantastic job. So thank you very much. Hey, now listen, you are going to be talking to, who have we got? We've got Sanjeev Gupta you're going to be talking to about Mars. Yep. Nobody knows more about Martian geology than Sanjeev. And we've got Andrew Coates as well from the Mullard Space Science Laboratory at UCL.
Yep.
So I'm going to hand it over to you and look forward to hearing what they've got to say.
Thank you so much. Well, yeah, I'm absolutely delighted to be here on behalf of Sky at Night to do this session on life on Mars. So, of course, the Sky at Night has been running for so long, and we have featured Mars pretty heavily over the years. So, just to introduce this session, I have prepared a short clip to kind of show you a bit of the coverage that we've had on Mars over the decades. So, if we could now show that brief clip to introduce it.
Since The Sky at Night started back in 1957, there have been about 50 episodes dedicated to Mars. Humanity has sent more probes to Mars than to anywhere else in the solar system. Mostly because for centuries we have been dreaming about the possibility of finding life on Mars. But have we been successful so far? Let's find out.
Percival Lowell. He was a wealthy American businessman and no mean astronomer. He discovered the planet Pluto, but he turned to Mars in the 1890s after seeing drawings by an Italian, Giovanni Schiaparelli, who had found faint linear features on the Martian surface. He called them channels. By 1900, Lowell had produced his own maps of Mars. He said Schiaparelli's canali really were canals, and the geometric and planet-wide construction implied the work of rare intelligence.
That Mars is inhabited by beings of some sort or other, we may consider as certain, as it is uncertain what those beings may be.
In 1965, Mariner 4 was the first mission to successfully fly by Mars, sending back close-up images of the surface of the red planet for the very first time. Each image had to be radio transmitted back to Earth, taking over 8 hours each. Images were sent in the form of binary code, with 240,000 bits of code representing the shading of 40,000 dots that made up the very first pictures of the surface of Mars.
The pictures and data recorded by Mariner 4 revealed Mars to be a cold, barren planet. The atmosphere contains little or no oxygen and appears to be composed largely of carbon dioxide. There were no obvious traces of the canals, no evidence of life forms, but the pictures cover only 1% of the Martian surface. And the exploration of Mars, begun by Mariner, will continue in the years ahead.
1976 could be the year of Mars, the year in which we solve one of the most dramatic problems in the whole of science. Is there life on Mars?
Viking did not detect life on Mars. In particular, Viking could detect no organic compounds in the soil.
There is a new picture of a new place on Mars. And for me, at least, that's the big payoff.
Curiosity's first goal is actually the goal of habitability. Were there conditions on ancient Mars that were suitable for life to have formed in, existed in, and been preserved in?
Over the decades, the focus of our Martian exploration missions has changed. We're now primarily looking for evidence of ancient life on Mars, and plans might be in the pipeline for sample return missions in future. One thing that's never changed, though, is our fascination with our nearest neighbour and our determination to understand its secrets. But will we one day go there? And if we do, what will we find?
So I am delighted to be joined by Professor Sanjeev Gupta, who is a planetary geologist from Imperial College London. We just saw you there in the clip, so thank you so much for joining us.
No, it's great, actually. Welcome. Wonderful.
Oh, thank you. We saw you there just now talking about Curiosity, and it was the Curiosity's early images that you were talking back in 2018. Curiosity's been on Mars for well over a decade now. So is it still going? What's happening with Curiosity?
Oh, yeah. So I was working on Curiosity only on Friday this week. So we're going well, exploring new terrain, absolutely fantastic results, new rocks to look at, new vistas. The scenery is beautiful at the moment as we're driving through the low-lying mountains. It's extraordinary, yeah.
Oh, brilliant. So what kinds of new results are we still getting from Curiosity then?
Well, it's interesting. We're getting new results about where we are at the moment. So we've been exploring the rocks we're currently at that are rich in sulfate rocks, and we're trying to work out what the ancient environments and the landscapes were like at the time. And we believe we're actually driving through a landscape that was mostly a desert, but sometimes there was water there, sometimes there were rivers there. But actually, our most exciting finding most recently has been from old data, right at the beginning of the mission. So the image you can see here
we show the image?
Yes.
Mm.
So this is an image of Curiosity at a place called Yellowknife Bay, which is one of the first places we explored, and we drilled there and we analyzed samples, but we weren't quite ready to search for organics. And so we actually, what we call doggy bagged a sample. We carried a sample on board, and people have been working out strategies and protocols for analyzing samples. And most recently, there was a publication that showed evidence for what we call long chain hydrocarbons, alkanes. So quite complex hydrocarbons, organic compounds in ancient sediments on Mars. Now we knew we had sort of smaller scale compounds. We discovered those earlier, but this is the first time after so long of quite complex organic compounds. And most recently, somebody's proposed that maybe this is quite an interesting result, because obviously Mars has been subject to radiation and organic molecules get destroyed by radiation. And so suggested that maybe these complex organic compounds are actually the breakdown products of even more complex organic compounds.
Oh, wow.
So could these be the signatures of life? And this is a hypothesis publication.
Okay.
Absolute hypothesis, is not proof in any way, but it gives us something to chase. And really what we would want is to analyze samples like this on Earth in Earth laboratories.
Absolutely. And I mean, it's fascinating, really, that like after all this time, we are still getting new results. And like you say, from old samples. So that's incredibly cool. Now, of course, Perseverance is the successor to Curiosity, and Perseverance is also already on Mars. And so Perseverance, one of the key missions is to find biosignatures. Can you just briefly explain what we mean by biosignatures?
So a biosignature is a feature, so many different definitions, but what I would understand is that a biosignature is a feature in a rock that can be attributed to life, basically. So it's formed as a result of the interaction of life with sediments or something like that. So that's really what it is. And we've had a very exciting discovery recently with Perseverance. We can flip back a slide very quickly. So this shows Perseverance at this locality, and the rocks you can see in the foreground just below are formed in an ancient river valley, and these are actually lake sediments. So these are sediments that were formed in an ancient lake that was a habitable environment that was suitable for life. And when we looked in detail at these sediments, and you can see Perseverance here showing off this drill hole she's proudly collected a sample for. But if you go to the next slide, what is amazing here and what immediately intrigued us is that in the center of this image, you can see this band of reddish colored rock. This is about a centimeter across. So you're looking at a really close-up image taken with our hand lens camera that's at the end of the arm. You can see these little dots here, these millimeter scale round circles. And you can see the reddish rocks. These are iron 3 rich. These are rich in oxidized iron. And then the dots are white in the center and they have a dark rim around them. What they're actually recording is chemical reactions that occurred in these rocks, in these sediments, billions of years ago, 3.7 billion years ago. And we call these reduction spots on Earth. So they're ubiquitous. We find these sorts of features in Earth rocks, even up in rocks in Scotland that are 1 billion years old. We can see this, rocks in Devon that are younger. And on Earth, these features typically form due to microbial interactions with sediment.
Wow.
So
That's...
yeah, amazing. So what this tells us is that we're not saying that this is life on Mars. What we're proposing is that these are potential biosignatures that were formed by either formed without biological processes, so abiotically, or they were formed through biological interactions on early Mars. And we can't prove this yet, so it's a hypothesis. And what we want is to have these samples back on Earth to analyze in Earth laboratories to be really sure about that. But it's the first time we've had something that could have been formed by life. And so therefore we're very, very excited.
Yeah, that is tremendously exciting. And I know that these were referred to in the media a lot as kind of the leopard spots. So it's a wonderful finding. Now, actually, you mentioned about how great it would be to have these back on Earth to study. And I know that Perseverance is storing samples. So what's the end goal there? What's the hope with all that stuff that Perseverance is storing?
So we've been collecting samples. We've mostly, in the belly of the beast, there's our rucksack, which is an amazing storage facility where all the tubes are stored with the samples we've collected. We've got a diversity of samples there. Unfortunately, what happened was that the cost of the sample return mission became very, very expensive. And this was a US-funded mission, and that's been, I would say, parked is the word, so rather than cancelled or anything. And so we hope that, and they're exploring different strategies to bring back these samples through less expensive ways, or even that humans go to Mars and bring these samples back. And that's one possibility. So who knows when they'll come back, but they are extraordinary samples that will tell us not only about life on, if life had occurred on Mars or not, whether these leopard spots are the signatures of life or not, but also many other questions about Mars's history that we can resolve by analyzing samples in Earth.
Yeah. Absolutely. I mean, that's the thing. We pack so much onto these rovers, but that is still limited. There is just so much more that we can do if we manage to get these samples back to Mars. I mean, just very briefly before we wrap up, I just want to ask you actually, because I know that there is a lot of talk about, the future of crewed missions in the solar system and potentially sending people to Mars. So where do you think we'll get the best scientific return? Do you think it would be sending crewed missions or working on those sample return missions so that we can actually get more rocks back on Earth?
So I think crewed missions are a long way off. I don't think that's going to happen in the immediate future. So I'd like to get these rocks that we've collected from a diversity of places back to Earth, analyzed in Earth laboratories. And even still, when we have crewed missions, those samples will still have to come back to Earth. They're not going to be analyzed on Mars. So imagine that's going to be a long time. So in many ways, by having these samples that we've collected on Mars currently, they will enable us to develop strategies, search strategies, laboratory strategies for how to handle and explore and examine samples and keep safe. We don't know what's in these samples, so we have to have this planetary protection. We have to protect Earth from anything that might be in these samples. That's not an easy thing to address. So I think I'd like these samples to come back to laboratories, and then we can develop and think future. Because even if we discovered evidence for life in these samples, people would maybe question that. There's always debate, basically. Scientists like to poke at any interpretations that are made. And so I think we would want to, see what emerges.
Absolutely. Well, Professor Gupta, thank you so much for speaking to me today. It's been absolutely amazing. I'm sure everybody who's tuned in has found this really exciting. So there's still so much more to learn from Curiosity and Perseverance. But thank you so much for your time.
Thank you.
So we heard there about these two amazing rovers, Curiosity and Perseverance, that are already on Mars and already doing amazing stuff. But there is actually more to come. So another rover, as part of the ExoMars mission, will be traveling towards Mars in the future. So we just have another short clip to introduce the ExoMars mission before we speak to our next guest. So if we can show that clip, please.
ExoMars is a two-phase mission. The first phase launched a decade ago, arriving at Mars 7 months later in October 2016. Phase 1 consisted of 2 parts: the Trace Gas Orbiter, or TGO, designed to study the Martian atmosphere from orbit, and the Schiaparelli Lander, designed to test a new landing system. On arrival, the 2 parts of the spacecraft separated so the lander could attempt to, land. Everything appeared to be going well. The lander entered the thin Martian atmosphere at 21,000 kilometers per hour, protected by its heat shields. The plan was to then deploy a 12-meter wide parachute to slow the lander down. After the parachute detached, this would then be followed by retro rockets to come in for a nice soft landing at walking speed. Unfortunately, contact with the lander was lost during this complex choreography, and images of the surface of Mars taken days later revealed its crash site. But while the lander was crashing, TGO was successfully settling into orbit around Mars. Its mission was to investigate a great Martian mystery, the presence of methane plumes detected several years previously. The mystery comes from the fact that scientists don't know for sure where this methane is coming from. Could it be life? Phase 2 of the ExoMars mission, the Rosalind Franklin rover, is now coming soon. With the launch currently planned for 2028, this phase has seen its fair share of delays due to funding changes and complex geopolitical challenges. But when it does finally land on the surface of the red planet, the Rosalind Franklin rover will be equipped with unique instruments which will allow us to investigate ancient life on Mars like never before. We don't think we will find any evidence of active life on Mars, but it is so exciting that we might find proof of microbial life that lived billions of years ago when the planet was wet. So with Phase 2 fast approaching, let's learn more about this unique new mission to Mars.
Well, I am now joined by Professor Andrew Coates, a planetary scientist at Mullard Space Science Laboratory and principal investigator of PanCam on the Rosalind Franklin rover. Thank you so much for joining us.
Pleasure.
So we saw there a brief introduction of the ExoMars mission. So you're a very big part of the ExoMars mission, which is going to be the next big thing to land on Mars. So tell us all about it.
Yes, this is the ExoMars rover, so the Rosalind Franklin rover, as it's now called. It's called Rosalind Franklin after the amazing X-ray crystallographer who made lots of discoveries about DNA. So with this mission, we're looking for life on Mars as well. And this has a really new aspect of drilling deep underneath the surface. This is part of a bigger program called the ExoMars program, and the first mission in that was the Trace Gas Orbiter, which has already made some really interesting discoveries. It was looking for methane, which is one of the things which could be produced by life. It hasn't found any. Other missions have, so that creates an interesting sort of question as to why is that. So that's research which is still underway. But with the Rosalind Franklin rover, and maybe if we go to the first slide, we can see a artist's impression of that on the surface of Mars. So we could we can actually see that. So the rover, it weighs 300 kilograms. It's going to land on the surface, be launched in 2028, landing on the surface in 2030. And you can see that's the rover there with its wheels at the bottom, of course. Top of the mast, that's PanCam, the panoramic camera system. And also underneath that is ENVIS, which is the infrared spectrometer. So actually the UK is playing a really big role in the Rosalind Franklin mission. It actually built the rover that was built at Airbus in Stevenage. PanCam, we led that from UCL, Mullard Space Science Lab, but it involves a number of universities in the UK and also colleagues in Germany and Austria and so on. So it's an international collaboration in itself. ENVIS, we actually had to build that in the UK. That's being built at the moment to replace a Russian instrument, which was going to be on there. So the mission has had a bit of a checkered history, but that's what happened. And actually, the next slide shows a nice animation of the ExoMars rover. So this shows it just rotating, just shows the solar panels. It's solar powered. There's a subsurface sounding radar, the cameras on the top, and the infrared spectrometer. So with that, we decide where to drill. The black thing on the front is a 2-meter drill. So we're drilling underneath the surface 2 meters, and that's the first time that will have been done on Mars.
Oh, that's absolutely amazing. Of course, like you mentioned, that the thing that really sets apart the Rosalind Franklin rover is the drilling, and drilling particularly deep. So why is it going to be useful to drill so deep?
Well, the surface of Mars is really inhospitable for Mars now because about 3.8 to 4 billion years ago, Mars actually lost its magnetic field, and that meant that its early atmosphere has sort of been leaking away because it's unprotected by a magnetic field for all that time. And so 3.8 to 4 billion years ago, Mars, we think, had habitable conditions, and that's about the time that life was starting on Earth. So we think there's the possibility of life starting on Mars then. So if we drill deep, we can get underneath where the surface of Mars, because of this thin atmosphere, is bathed by ultraviolet radiation, also radiation from space, from the sun and the galaxy. So it makes it a really inhospitable place. Also, because of the thin atmosphere, the temperature is low, so maybe 0 to 10 degrees on a good day, and
Oh, wow.
100 to 120 degrees centigrade at night. So everything that you put on the surface of Mars has to survive that amazing temperature range, and so we need amazing engineers to actually work with us to produce the the circuit boards and the cameras and so on, which can actually survive that temperature. And we really have to test that to make sure it works.
Of course. I find it so fascinating that we can know 3.8 to 4 billion years ago. Obviously, that's, it's still a big range, but like it just feels incredible that we can know that happened then.
Yeah, the way that was found out is actually from measuring the magnetic field of Mars. So that was done for the first time around about near 2000 mark. And so that was by one of the earlier missions. And so that found crustal magnetic fields, or remnant magnetic fields, in the Southern Highlands region, which is old. And you know that by counting craters, knowing the cratering density. So we know it's a very old terrain in the Southern Hemisphere, but a much lower and younger terrain in the Northern Hemisphere, which might have actually had water in that in earlier times. So the 3.8 billion years to 4 billion years is from the measurement of that magnetic field.
Well, that's incredible. And so whereabouts is Rosalind Franklin going to be landing? Is it going to be close to Perseverance or somewhere different entirely?
It's about 1,000 kilometers away, and about 1,000 kilometers west, actually, of where Perseverance has landed. And actually, the next slide shows the landing position. So it's called Oxyoplanum. It's actually slightly older than the Perseverance landing site, about 4 billion years. It's got signs of clays on the surface, which have been seen from orbit, phyllosilicates as they're called, and so a similar sort of terrain to that. But this is an amazing place. It seems to be, on the edge of what might have been a global ocean in the north. There were some recent results from the Chinese rover actually on Mars, which showed that there may well have been a very long-lived body of water in the northern hemisphere. So very important.
Sorry, can we show the next image so that because I think you were pointing to the map.
Oh yes. The next absolutely. This image shows.
There we go. Yes.
Oxyoplanum location where we're going to be landing, and it's sort of pinpointed on the left-hand side, so that's a global image of Mars, and this is a particular area with an outflow channel where we know that water was flowing outwards around about 3.8 to 4 billion years ago. It's an amazingly interesting location, as is the Perseverance landing site, and of course Curiosity as well. But this site could have been actually a beach. It might have been water lapping on the surface of Mars 3.8 to 4 billion years ago, and so and also water coming down from this outflow channel. So this means that the water would have been collected over a large area, and there would have been the possibility of bringing anything which was on Mars into this area. So drilling deep is really important. The 4 billion years is a very important time, and so this is why we're searching back that long.
Oh, that's absolutely incredible. So I think we're probably going to have to wrap up. But what I just did want to ask very quickly before we go, the same question that I asked Professor Gupta actually. Just like there's a lot of discourse, especially from people like maybe the CEO of SpaceX, talking about sending people to Mars. So how do you feel that our funds would be best spent in the future? Do you think that we should be investing in things like sample return missions, or looking to send people to Mars?
Well, for me, our very best exploration is done robotically. So yes, absolutely, sample return of those samples from Perseverance would be really important to get those back to Earth. Robotic exploration like Rosalind Franklin, also, drilling underneath the surface, looking for signs of life. I think for me, actually, personally, I would not like to send people to Mars yet. Elon Musk or the CEO of SpaceX has talked about sending 1 million people to Mars. I think that's a we're not going to be doing that yet. If we did something like that, we would contaminate Mars to a huge extent. The worst thing you can do is contaminate Mars. We're trying to understand whether there could ever have been life on Mars. You don't want to be taking life to Mars and measuring that. So we have to be very careful with our instruments and with the rover as well, to make sure that it's sterilized and not contaminating the surface. And sending people, I think, for me, would be the final contamination.
Absolutely, I completely agree. We keep Mars pristine for as long as we possibly can. Professor Coates, thank you so much for your time and for telling us all about ExoMars. I absolutely cannot wait for this to launch in 2028. So thank you so much, and bye-bye.
Thank you.
So that's been absolutely amazing. Were you guys watching?
That was absolutely incredible. 2 fantastic talks. Thank you, George. I would actually just, what Andrew said just there at the end, talking about not contaminating Mars. We talk so much about when are we going to go to Mars? How are we going to get to Mars? Maybe we should never go to Mars. Maybe we should just say, okay, we're going to just keep Mars pristine. I mean, I would volunteer to go, and I promise I'd wash my hands and clean my shoes and everything. But I don't know, maybe we should just say, okay, we'll keep it pristine. What do you think, Susie?
Well, firstly, sending people to Mars would probably not do their health any good right now anyway. So I think I don't have to worry about that imminently. I'm not sure there's going to be 1 million people en route anytime soon. And in the meantime, I think the important thing to do would be continue our robotic exploration of Mars so that we can collect as much information about the pristine planet as we can before humans get there. I don't think you can ever say we should never send humans there, but I think we should do all we can to find out about it before we do.
Yeah, I was thinking about the Mars sample returns and that mission that's now been parked or put on hold because it was too expensive. There's going to be those little test tubes of Mars samples lying around the Martian surface. And I think about future space archaeologists that discover them and go, what the hell are these?
What were they doing?
What are these people thinking about?
Yeah, absolutely. And I think, to be honest, I mean, I completely agree. I think that sample return missions is where it's at. You know, bring the space rocks home, but do it all robotically. Because, I mean, while there is, you know, just like at the moment, we think, you know, no real chance of finding active life. We don't know what's below the surface. We don't know what's there. And there are actually things in place. There's a legal framework in place for what happens if you were to find active life anywhere in the solar system, to kind of protect that from contamination from Earth, but also protect life on Earth from contamination from extraterrestrial life. Yeah. So really, I mean, I think it's amazing to know about these things, but let's leave it alone.
Well, we have at Leicester actually one of the double wall isolators that is an environment within which we could explore a sample that came back to the Earth. So we've built a huge facility to receive Mars samples and make sure that we can explore those samples without contaminating them with the Earth and the life on the Earth. And that if there were to be anything in those samples that could contaminate the Earth, that wouldn't happen. So actually it's really interesting to think that it works in both directions. We don't want to contaminate the sample or the Earth.
I sense I sense a movie happening here, a disaster movie.
Yeah, that could be. That could be, yes.
I might get a badge made for you, George, and the Sky Night presents with "Bring the Mars rocks home."
Yes.
I think that would be good.
Yeah, definitely.
How long have we got? Have we got time for questions?
Yeah,
for
we've got time for a few questions. I mean, got some quite good ones in here.
Well, let's start with a kind of Mars 101 question for you. Why is Mars called the red planet?
Oh, so Mars is called the red planet because it appears red. So the surface of Mars, so we've actually got these really beautiful images that we've got from lots of the rovers, but the surface of Mars just has this kind of this dust all over it that appears red. So, I mean, I'm guessing that is because of some oxidization.
Yes, I think it's an iron oxide.
Yeah, it's rust, exactly.
It's a rusty planet.
Exactly. And
there we go.
A few questions around kind of what happens to these rovers at the end of their life. And I think that's always kind of an interesting thing to discuss when we're talking about sustainability and how we leave the smallest impact we can. So obviously, we're not bringing these rovers back. They're going to sit on the surface until...
Forever.
Yeah, forever. Sorry, go ahead.
So I wonder if this kind of, falls under similar terrain as kind of space debris in general, because we have so much space debris, in our orbit from all these defunct satellites. So, we've put thousands of satellites into orbit and lots of them not used anymore, and they just kind of float around there forever. But yeah, I mean, the stuff on Mars that we've sent that stops functioning, whether it's because it's reached the end of its mission lifetime or because, there was a mission failure, it is just stuck back there. So it's just space junk that we are sending out to Mars, and it will just remain there. There is no plan in place to bring this stuff home.
Yeah, and there wouldn't be, because it would be far too energetically. It would cost far too much energetically to bring it back. But also,
Yeah.
we know when we send, I work on a mission to Mercury, and at the end of the mission lifetime, we're not bringing this spacecraft back from Mercury again. It would take so much energy to do that. But what we will do is be very careful at the end of its life. We'll crash our spacecraft into the surface so that we make a small new crater on the surface of Mercury that contains all of the things that we sent. We won't contaminate the environment by risking it colliding with anything else or breaking up into pieces. We're pretty careful. Same with the Earth missions. NASA and ESA, our missions that we launch, we're very careful about the end of life for those satellites. And
well, there's a spot in the South Atlantic. It's called the point of inaccessibility. It's the most remote point on Earth, the furthest from land, and there's a little point that's known as the satellite graveyard. So when they're deorbiting satellites, there's a special point just sort of off the Falkland Islands where there is a whole collection of space junk lying at the bottom of the sea.
I mean, that's true, but I don't even like that particularly.
No.
I'm not a big fan of bringing these
still
things
not
back
great.
and hitting the ocean. I'm also not a fan of them burning up in the atmosphere, because you get sort of heavy metals injected into the upper atmosphere. We're still not sure what the impact of that is. I'm not a fan of putting things in something called a graveyard orbit, which is just boosting the orbit so it's out of the way of other things.
Yeah.
I don't think we yet know, especially with the number of launches we're doing now, the problem's becoming worse. I don't think we really know what to do with our instruments and satellites at the end of their life. It's a really interesting sort of debate, isn't it?
Anyway, that was a question from Jasper, year 5.
Year
He
5.
wanted to know whether
Thank you,
abandoned-
Jasper.
That,
Wow.
that took us
It's
into
a
quite a
great question.
philosophical
It's
discussion.
a great question, isn't it? Year 5,
Really.
crikey.
Really.
Listen, I wasn't thinking about things like that when I was in year 5. So
I just read this question. It said, to confirm, we'll return at 11:45. And I realised that was Angie over there.
Yeah, that's
We
Angie
got-
over
we got
there.
the time wrong.
reminding me about the time, yeah.
So where else are we?
Well, that's a good one. What is the probability that the Rosalind Franklin rover will land successfully on Mars, given the mishaps of Beagle and Schiaparelli?
Oh, it's a good. Well, landing on Mars is hard. I mean,
Yeah,
it's
that's what we've
really, really
learned.
difficult. So, yeah, what do you think, George?
So I would say that, yes, Schiaparelli, it did not go according to plan, but there were really key lessons learned from it. So
Yes.
the specific ways in which it failed have kind of allowed us to learn so that we can prevent those specific failures next time. Obviously, it's hard to anticipate failures that we've never seen before.
Exactly.
And one thing that's always challenging is like, what's the weather going to be like, stuff like that. But also sites are chosen thinking about, the atmosphere in those places and the likelihood of sandstorms and dust storms. So hopefully the lessons learned will mean that, we don't have a similar disaster.
I love your optimism, and I agree with you. Yes, we should be optimistic.
It's worth pointing out, someone again asking about how do we get the samples back. We do get bits of Mars coming to Earth, which I find absolutely extraordinary. The fact that you will have impacts on Earth, which will send debris beyond the escape velocity of Mars, will find its way to Earth and
Impacts on Mars.
impacts on Mars, sorry, and will find its way back to Earth. Not only that, but clever scientists will be wandering around and pick one up and find it. And I think to myself, what are the chances of that? But we get Martian meteorites here.
We do. Don't
It's a
pick them
must.
up.
Don't pick them. Why shouldn't we pick them up? Shouldn't we pick
Well, we're
them up?
going to contaminate them really, really quickly with
Well, they're
microbes.
pretty kind of burnt up anyway. So,
They are
so it's
quite-
not like pristine Mars, is it?
Yeah, no, it's definitely not pristine Mars. But the less they're handled, the better. I think
Yes.
probably meteorite scientists would say. That would be my guess.
Okay.
Right, yeah.
How are we getting on? How are we getting on for time?
I think we basically are out of time. To be
Okay.
honest. So, George, thank you so much for joining us. That was a really lovely conversation that you had. So
Oh, thank you so much for having me.
It's a pleasure. I'm a bit jealous because talking to Sanjeev and Andrew is one of those conversations you could just spend all day. They're so
lovely.
knowledgeable and terrific.
Oh yeah, absolutely. Like honestly, we could have talked with both of them for so much
Yeah.
longer. We had so many bits to talk about.
Oh, that's
Yes, and yourself, of course. And good luck with the show.
Yes.
May you continue for another 15
We look
billion
forward
years.
to the next episode.
Yeah.
Thank you so much. All the
George.
best. Bye-bye.
Bye.
Bye.
Bye.